For the remaining subchapters, we are going to discuss on the performance improvement method for Brayton cycle. Subchapter 5.4, the Brayton cycle with regeneration. If we look at the simple Brayton cycle diagram, we can see that the temperature at the turbine exit is greater than the temperature of the compressor exit. Instead of wasting this high temperature gas to the ambient, it will be better if the heat of this high temperature gas can be transferred to the lower air leaving the compressor. Therefore, a regenerator will be placed between the hot gas leaving the turbine and the cooler compressed air leaving the compressor. And this method is called regeneration. Now let's have a look at the schematic diagram and the TS diagram for the Brayton cycle with regeneration. First, the fresh air will enter the compressor to be compressed. The compressed air will then enter the regenerator, where the temperature of the compressed air will increase. Leaving the regenerator, the air will enter the combustion chamber. The air will be mixed with fuel and combustion will occur. The result will further increase the temperature of the gas. The temperature of the gas leaving the combustion chamber is the highest temperature for the cycle. Leaving the combustion chamber, the gas will then enter the turbine and being expanded, where the pressure and temperature of the gas will drop. During this process, work will be produced by the turbine. After exiting the turbine, the gas will flow through the regenerator before it will be exhausted to the atmosphere. Again, the temperature leaving the turbine at state 4 is higher than the temperature leaving the compressor at state 2. Note that regenerator is a kind of heat exchanger device that have two flows. Flow from the turbine exit and flow from compressor exit. Since the turbine exit having higher temperature than flows from compressor exit, therefore heat will be transferred from high temperature region to low temperature region. The heat received in the regenerator is called Q regen. Meanwhile, instead of exhausting the gas with this amount of heat, by using regenerator, we can save this amount of heat which has been transferred to the compressed air. Note that Q regen is equal to Q saved. In order to analyze the regenerative cycle, we can use regenerator effectiveness epsilon regen. Regenerator effectiveness is the ratio between the heat that is being transferred to the compressed air to the maximum heat that can be transferred. For a heat exchanger, the steady flow energy equation for the Q regeneration will become this expression. Heat transfer during the regeneration process is equal to enthalpy at the outlet minus enthalpy at the inlet. We obtain this equation since we neglect the changes in kinetic and potential energy. The heat exchanger is not a work-producing device or work-consuming device, and due to process 2 to 5 that will receive heat from the process 4 to 6. Therefore, Q regen is equal to enthalpy at state 5 minus the enthalpy at state 2. And for gases, the equation will now become heat transfer during the regeneration is equal to Cp times temperature at state 5 minus the temperature at state 2. The maximum possible temperature leaving the regenerator is equal to the temperature at state 4, T4, if the heat transfer process is very efficient. Temperature at state 5' is the maximum temperature that the regenerator can have, and it is equal to the temperature at state 4, T4. However, in most cases, the temperature leaving the regenerator will be lower than the temperature at state 4. Temperature at state 5, T5, represents the common temperature leaving the regenerator. We can now develop the relation for the maximum Q regen. The regenerator effectiveness will be this expression. For the heat added into the cycle, it occurs during the process 5 to 3. Since the heat transfer in is equal to the enthalpy at the outlet minus the enthalpy at the inlet, therefore Q in is equal to Cp times T3 minus T5. Note that the heat save Q save is equal to the regeneration heat Q regen. In other words, Q save is the portion of heat that leaves the system before it is being added to the regenerator. From the steady flow energy equation, we will obtain this expression. Again, since Q save is equal to Q regen, we can have this relation. The heat that is rejected to the atmosphere considered occur at state 6 to 1. Therefore, the steady flow energy equation analysis will give us Q out equal to Cp times T6 minus T1. We also know that in the actual case, the process across the compressor and turbine are not isentropic. If given to us the isentropic efficiency for the devices, we can determine the actual properties leaving the compressor and turbine. The actual power input and power output will use the actual properties to be determined. We also can calculate the actual regenerator effectiveness by using the actual properties, which for our case is the state 2A and state 4A. Again, we're still going to use the same formula for the thermal efficiency to the Brayton cycle with regeneration.